we're going to do a little quick run through of kind of the start and the story of the competition. So this will be a little redundant for those of you that already competed, but we want to give a preface for those that are coming in a little later or didn't compete at all. So give me 1 second, I'm going to put this up here. And we're going to go through, first we're going to do all the main story challenges. So a lot of people got a good chunk of the way through the main story at the competition. Give us a second to boot in. Okay, so we're going to go here. All right, so we're going to start with a brief history of Razor Power Company. This is what we went over at the start of the competition on Saturday morning. So for those of you that don't know, the past of Razor Power Company was established in 2023 as the leading solar energy company in Northwest Arkansas. But things didn't go so smoothly during their inaugural year. Our beloved maintenance man, Barry Chip, fell for a phishing email when he was downloaded an Excel file that had some macros in it, which downloaded some malware, and the intruder was able to capture his password and kind of wreak havoc on the company. Needless to say, Barry Chip is no longer with us here at Razor Power Company. But however, with the help of last year's volunteers and outside contractors, we were able to stabilize Razor Power Company. Next, the future, Razor Power Company 2024. Since the incident in 2023, the leadership has since shifted focus to a more secure and robust form of energy, nuclear power, right? That's the best thing for a company that just had a cyber intrusion, right? Nuclear power. The past 6 months, they had spent countless hours testing and configuring and recommissioning their nuclear reactors to get them up and running. So on October 1st, they started up the reactors for the first time, providing clean energy for all of NWA. However, in the rush to get their reactors up and running, our CIO, Shane Barnabas, started to question their security and kind of what was going on. So he contracted the teams showed up to be contractors for Razor Power Company. So this was the letter that everybody received on the opening banquet, telling them that they'd be hired to secretly try to ascertain the issues that were going on at Razor Power Company, and kind of figure out if there was actually danger, and if so, how can we stop it? So the task that everybody was tasked with was to go through and complete all these work orders that they had been tasked with, and try to figure out, what was going on. And Shane communicated with them along with other employees, which was the game masters, with them along the way to fix different issues that were going on. So this was kind of the setup. We had main story and we had the side quest challenges. Today we're mainly going to be going over the ones that fall in the main quest challenge. So first, Gideon, do you want to pull up, do you have the NetLab stuff pulled up already, right? The NetLab box.
The VM?
Kali box.
The Kali, oh.
Yeah.
I don't even want me to pull up the Kali VM.
Real quick.
I will do that.
So, the first one, what I'll do is I will show you all, those of you that did not get to compete, the first challenge that competitors had to complete. I'll pull it up in here in a second. So, the first challenge that we had people complete was a good student always does his homework. So this challenge basically is we had a virtual environment for them, right? Which contains 3 Kali boxes for the team members to use, as well as a network that it was attached to. And so the first thing that you want to do if you're in a scenario like, okay, I need to figure out, what's going on with this company. They didn't give me any briefing documents. I don't know what's on the network. Let's do some scans of the networks.
Yeah.
So the first challenge that they had to do was identify all the hosts that were up on the network. So in order to do this, So in order to do this, one of the most common tools that I'm sure most of you have heard of, this is the Kali box that they were given access to, is Nmap, right? So Nmap is a vulnerability scanning tool, a host scanning tool, a network scanning tool that's very commonly used. So this is the machine that we're given with. It's a blank Kali Linux machine. Kali Linux comes installed with many common tools. One of the things we can do first, I'm like, okay, see what our IP is. So we're on a .2/24 subnet. So we're gonna run, the first thing that we're gonna run would be, Nmap, and then SL. So SL means that we're going to list all the active hosts that are up on the subnet, and then we need to specify what subnet that is. So that's going to be .2/24, right? So we can see here that our current address is .2.15. That's for this current machine, and it's a /24 subnet. So the subnet definition is going to be that. So we're going to run that command, put in our password for Kali.
No, I think you typed
That's because I was doing that. Oh, let's see here. I also have a write-up of this so I can show you guys what we're looking for. Okay. Let's try this again. There we go. Okay. So this is what we were looking for before. I just had the wrong thing. It was supposed to be N instead of L. So N will list out all just the active hosts that are up on the network. So this finds us 15 hosts from .1, .2, .16, .17, 135, all the way up. So now what we want to go back to doing is we're going to enumerate all the hosts, all the services on the host. So that what this is going to do is it's going to scan all the open ports that are on each of the machines. There's a lot of different options for Nmap. If you go to nmap-help, you can see that there's a lot of different types of scans that you can do. So this one that we're going to be doing is just a service detection probe, and it's going to try and detect what services is running on that machine. So we're going to go to speed, and do and start that again, and that'll keep going. So while we wait for that to go, so one of the issues that a lot of people ran into with this particular problem was that with a typical port scan, does anybody else, well, I'll ask this question first. Does anybody know off the top of their head what the available range of port numbers is? Like what's the lowest number you can have and what's the highest number you can have?
0 to 65,536.
Yes. So one of the interesting things is that Nmap by default is only going to scan the first 1,000 to 10,000 ports because those are the most common ports. So a lot of people, what they'll do is they'll do, okay, Nmap-sb for the subnet, and they'll go ahead and do that. But the thing is that's going to miss any ports that are over 10,000. So what you have to do to make sure that you get all those ports is you have to do a -p-p or -p-, which tells Nmap to go through every single port for every single host that's on the network. And this is taking a freaking minute, longer than it usually does. And so by doing that, then you'll search through every single port that you have on the network. And one of the ports that we had for one of Greg's services actually was on port 11,543. There we go. Which was what people were missing. So here we can see all the results. So we had like port 9,999. You'll notice this big blurb of text. So this was one of our custom TCP servers for like one of the math challenges that I made. And so it doesn't recognize what it is. And it's like putting out all the text from what the server sends to the client, right? Because it's probing it. But you can see a lot of, so for the other hosts that are down, it's gonna say not shown, closed ports. We have 998, 99, or 5,000, all these different ports here. But we're missing that one 1153. So if we go to, I believe it is actually .180. So you can see all 1,000 ports, scanned ports, are in ignored state, but it's only talking about the first 1,000 ports. So if we want to get That last port, we have to do -P, or -P-, and that will go through and scan everything. To get that all up. But do you want to start talking about kind of your the next series? So once you finish that, you've mapped all the services, you would notice that you would get a PCAP. And so for the next challenge, you're going to be analyzing this PCAP of traffic from this network and trying to see if there's anything malicious going on. So you can probably X that out for now.
Yeah,
and then while that runs, you can start explaining the next challenge.
Okay. So, for those of you that I haven't met this year, I am a former CyberHogs officer. My name's Gideon, and I had the pleasure of being one of the game masters this year. Yeah. So. Yeah. So the next challenge of the first suite of challenges is first contact. So we see our message here from our Shane Barnabas saying, we've been noticing some weird traffic on the IT network and narrowed it down to the time frame provided in the attached packet capture. Our web server started glitching around it. Can you let us know what you find? And at the bottom we see we have this capture.pcapng. So I already have this downloaded, so I'm going to open this up. And this opens up in Wireshark. So by quick show of hands, who here has used Wireshark before? It's just out of curiosity. Okay, so a good chunk of you. That's good. So Wireshark is a tool used for analyzing live or past traffic packet captures. Okay, so packets being information that's traveling back and forth between devices on the internet. And as the challenge message states, they've narrowed the range, or Shane, Razor Power Company has narrowed the attack to have happened within this specific time range provided in this capture. So, am I speaking to?
There you go.
Okay. I'm sorry for speaking to one, guys. So they narrowed it down to have occurring within this range. So upon opening it, you might think to yourself, okay, well, where the heck do I go from here? I see a bunch of, especially for those of you who haven't used Wireshark before, there's a bunch of information. It's like, okay, here's a bunch of, lots of different colors, lots of information. I don't really know where to go from here. Okay, so a few things to notice whenever you're using Wireshark to analyze different traffic is you need to identify the fundamental unit at each level is, or at each one of these different rows is each individual packet. And so we can, Wireshark identifies a few different features of interest that we can see for each packet, and that is the number of the packet in the sequence from basically however many packets from the start of the packet capture, the time since the start of the packet capture. So we can see for this packet, specifically, this is the 50-second packet. This packet occurred 6.4 seconds after they started the capture. We can identify the source and the destination IP. We can identify the protocol. That's going to be very important here in a second. It's supposed to tip off to is to look at web traffic in specific, which would be HTTP traffic or HTTPS traffic. So at the top here, you can see this. Hopefully, you'll see that at the very top. It says apply a display filter. Okay, and so that is the lifeblood for using Wireshark. Otherwise, you're just kind of left with this monsoon of traffic information. So if we want to filter by web traffic, all we have to do is type in, or specifically HTTP traffic, all we have to do is type in HTTP. You'll notice that whenever it's an invalid filter, it'll be red, but the moment that we type out something that is legible, it turns green. So then we go ahead and press enter. And if you'll notice, and well, it may be actually hard to notice, I'll go back to by default. Look at this little slider on the right, it might be hard to tell, but there's a lot of information here, okay? Specifically around 11,000 packets. So For anyone who tried to do that manually, God bless your soul. Hopefully no one did that. But if we narrow it down, the slider on the right becomes much more manageable. And so we can just do some diving. So we can, if we scroll down, just looking at this info section, just a first glance to see if there's any information of interest. We see something pretty unusual here at packet 8200. You'll notice that it says username and then a bunch of passwords, okay? If you ever see this in web traffic, that is very bad. Something not good has occurred. And so we can also see that the length of this packet is very high, but that's not super important. The biggest thing is to note that there's a bunch of these usernames. So if we open up this information in the bottom right, this actual packet itself, just click on the usernames, we can see that all these usernames have been dumped as well as the passwords. So yeah, the usernames and the passwords have been dumped from the web server. That is very not good. An attack has occurred. So if you remember the flag requirements, all you need to do is put in the packet number and you have your flag. The problem is that this is the result of the attack, but not the attack itself. We don't know why specifically it happened. And if we go a few earlier, and we do some looking, we minimize some of this, you'll notice that there is some questionable stuff happening on a web server, specifically that someone's trying to use SQL injection. So you can see someone types in username admin or 1 = 1 -- and then some random password. It means that they try to use an SQL injection attack. And if we can see, if we look earlier, they tried to do it a few different times. So by looking at this, we can see that they tried 2 times unsuccessfully, and then after this time, they dumped all the credentials. So using that kind of logic, if we're trying to figure out at which point the attack occurred, we can then kind of infer that at this packet 8186, where, if I minimize this, where the attacker was successfully able to carry out the SQL injection, and then the credentials are done. So the answer to this was flag 8186. Yes.
Can you explain why people might be looking at HTTP traffic rather than the other traffic when they're like initially scoping out what they should be looking for?
Yeah, I think I briefly, maybe I need to reiterate this, but in the challenge description, specifying that the web server was glitching out, that's the main thing that's the main thing that tips off that we should be looking at HTTP traffic rather than any other traffic. So with that in mind, hopefully y'all were able to find this flag. That leads us, yes, great.
One more thing, you know, password hashes.
Yes, these are password hashes, not the passwords, which will be relevant to, if I can show this. This is relevant to the next challenge. So I guess we'll just go ahead and get into that. So congrats, y'all solved the first contact challenge. Good stuff. Round of applause. Okay, now we have the next challenge, cats out of the bag. So Shane is clearly not happy about what occurred. An SQL injection dumped user credentials. This is bad news. Can you see if any of the passwords are vulnerable to hash cracking? Hopefully everyone followed proper password etiquette and didn't use a commonly used password. So the challenge is to find the vulnerable password and crack its hash. And the flag format is flag and then plain text what the password is. So given that we have all of these, given that we have all these passwords, the goal is to crack these hashes and figure out which one is a vulnerable or commonly used password. And so to do this, a common method to do this is using what we call a word list. So word lists are often massive, huge files full of leaked passwords. And there was a very famous one called the RockU word list. And so within Kali Linux, I quote my WSO, there's actually there's a specific directory for word lists. least for mine, it only has the rocku.txt. So given that this is a list of commonly used passwords, we need to figure out which one of the passwords is a commonly used password. This is going to be a great service to us. The other question is though, okay, well we have a list of passwords in this rocku word list, and we have the password hashes from the dump. Well, how do we figure out which one of these hashes is a commonly used password? And so, to do this, we'll use a hash cracker, and specifically, as the pun in the name suggests, which may not be super obvious, but cat's out of the bag, there is a tool called hashcat. And so, with that, I'm gonna go ahead and fire up hashcat. So, we'll type in hashcat, just press enter, and we'll, maybe if I type in -help, get an idea of where we should go. Okay, scroll to the top here, a lot of stuff. Okay, we can see the format, hashcat, we enter the hash file, it's gonna be our, it's gonna be the dump hashes from the web server, and then we enter a dictionary, mask, or directory. Okay, so in our case, then we should be able to do type, well, but behind the scenes, what you would do is take all the different hashes from that packet and you put them into a text file. You kind of clean it up, and what I have is on each different lines, there's a different hash. Knowing what type of hash these hashes is important. There's a tool within Kali Linux called, and I didn't know this until working on this challenge, there's something called hash identifier. So all you have to do is copy and paste one of these hashes. If I can copy and paste it, and just press enter. And the possible hash is MD5, which is a super common hash. So what we're gonna do is go to hashcat, go back to that, or I can scroll back up to go look at what other syntax rules we need. And so we have this basic examples, super useful. Thank you, hashcat, for this. We can see that if we want to use a word list like we are using, we can do hashcat -a0 -m, which -m stands for the hash type, and then we have the hash itself, and then the word list. So in our case, if you look at this massive list of hashes, you can scroll through and through to find, okay, well, hash mode 0 is MD5. Terrific. So just scroll all the way down here and just type in. This was giving me issues last time I ran this, so knowing us, it's probably going to break again, but fingers crossed, everyone, that this works the first time. So -d0 for word list, -m0 for MD5 hash, and a.txt is where I store those password hashes from the dump, and then /user /share /word list /rocku.txt, and we press enter. See if we got our hash. Actually, what I'll do, I think this will be foolproof. I'll do -show -0. I'll do result.txt. Basically, what this does is stores the output into a text file. So if I run this, ls, I can see we have this result.txt. We can see that corresponding to this hash, we got a password, which was I love me too. And so that's it, that's the answer. So the answer is flag, I love me too. And you cracked the password.
Woo!
Good job, everyone. You did it. Okay. And that is the first contacting cats out the bag challenge. So thank you. I will pass it on to
Me again.
to Henry.
2 seconds to get it pulled up, and then Okay, so the next challenge that we have for everybody in the main storyline is someone's always got to fall for an email scam. So we know that he stole a password. This password was for one of Razor Power Company's HR officials, or sales officials, if I remember correctly, Aiden. And so we want to know what he did with Aiden's credentials. He didn't have much access, thankfully, to privileged things, but it doesn't mean he still couldn't do something. So Shane gives you the idea that he might have tried to maybe send an email posing as Aiden, maybe try to get some other access through that way. So this challenge gives you a .image file, a disk image file, of the mail server, of Aiden's mail server, or his user account. And it asks you to see what you can find, do a little digging, and digging around and see what you can do. So if you're given a disk image file, one of the first things you want to do, just let me undo this. Clean this up. Actually, hold on, let me just duplicate my screen real quick so this is easier. Duplicate. Keep changes. And this is the write-up that you guys will get access to if you go over there. So let's see here. So, what are the first things you're going to see? So that image file here, RPCode, let me zoom this in a little bit so you get a better view. It does not want to be explicit. So one of the first things you're going to get is this image.gz. That just means it's compressed to GZ. And so you're going to decompress that image. And you're going to get rpco-hamilton.image. So one of the first things that you're going to want to try and do, there's a couple of different ways you can look through disk image files. I believe 7-zip, you can just put it into 7-zip. And you can just put it into 7-zip and kind of scroll through the directories. But one of the other things that you can do is you can mount the file. So what we can do, I already have it mounted on here. So what you would do though is you would make a directory on your mount directory. It'd be some name. So we can do test. And then what you would do is you would go mount-o-loop. What that does, the loop, the -o-loop, loop is just a device that is used to go through the directories of the image and mount it on to your device. That's all that is. And then I believe you do the image that you want to mount, like that. And then we're going to do it to that .test directory there. So let's go into it. Test. So we're in the image now. We can see that there's two things here. We can see that there's A. Hamilton's user account, right? On this machine that this image is taken from. So we're told in the description that we think it might be an emo thing. So let's first go into A. Hamilton and see what's there. So we got the usual desktop documents, downloads, mail directory. So maildir is a specific type of mailbox. It's just a mailbox format. There's two different types. Maildir is one of them. The other one is mailbox or something like that. I can't remember exactly what the name of it is. So obviously we're going to be looking at something there. So let's go into maildir. Well, we ls. Okay, what's in here? We got some what look like utility files or configuration files, and then we have three directories: cur, temp, and new. So let's just check one of those out. Okay, we have what looks like two random files. Let's print one of those out. 6468. Okay, so this just seems to be a normal file, a normal email file. Okay, so that's something. But these are probably not what we're going to be looking for. You know, if we're looking for, this is current files, right? This is what he has in his inbox. We're looking for something that the attacker might have sent. But what we're seeing here, The temp file, that's probably for drafts. The new file, that's probably for mail that hasn't been read yet. Okay, so what's one way that we could list all the files, right? Because when we do ls, it's not gonna list all the files that are in a directory. So what you have to do is if you do ls-la, which means list all, we can see all the files, and you'll see two new directories pop up, .sent and .trash. So we're thinking he sent an email to someone, right? So let's go to .sent. Let's look in there. Okay, same thing, current new intent. Let's go current. All right, so we also have two files in here. Let's see if we print out one of those 3824. What we have. Well, that one's not complete, so that's probably garbage. Let's try the other one. We have two options, I believe 3858. Then tap that. All right, so there's the first file that we're looking for, right? So all we had to do was figure out, that there was a hidden directory that we had to be looking for that had the .sent, and we get our flag for our new employees. So the second challenge that we are tasked with.
I have a quick question.
Yeah.
Could you use -H and with that show the sent files? So -LA.
Let's see. ls-h is that what you said? Nope. But let's see how it goes. So after that, the next challenge that people had. All right, so we knew they sent an email to one of our HR people, Marzell Mickey, who's kind of our HR manager at Razor Power Company. So the next thing that they need to do is, well, agent might not have known to look in his hidden directory sent file, right, to look at that email. But if he gets an email back from Marzell in his inbox, he's going to see that immediately and be like, what's up? So if the intruder was smart, he was probably monitoring their inbox to delete that email when it came back in to get rid of it. So that way Aiden didn't get tipped off to what was going on. So now what Shane wants you to do is figure out if there was a deleted file on that image, right? To see if he deleted one of the emails and see what pops up. You'll notice that there's an additional file on this problem, and that's going to be important. So you have the same image file as before, and you have an example of one of the email files that we saw on the Linux machine. So this is having you use some forensics tools. So let me clear my output tool. So most people's minds goes immediately to, okay, how can I recover files from a computer? There's a lot of tools out there to do it. Foremost is a very popular one, Scalpel, Excellent Autopsy, Excellent Elite. There's a bunch of online tools, a lot of things you can use. And the way that these work, that these file image recovery tools work, is they look for a header and a footer of a file within a given image. So if you didn't know, when you delete a file, it actually doesn't delete it. All it does is remove the reference to it. And so with the reference gone, it's deleted, but the information is still on the disk until it is rewritten, right? So if you don't use a lot of the space on your disk, you might not rewrite that part of the disk for a long time. And so that's what these tools take advantage of. They read byte by byte over the course of your image to look for these headers. So the reason I gave you a copy of that email file is because what I wanted you to do was find the header for that file. So what the header is, I believe I have an example of it if I scroll far enough back up into my console logs. There we go. So this is an example of how you would do that. So one of the ways you can do it is you can use the function head and get let's get the first 8 bytes, and we're going to pipe that to hex dump. So what hex dump does is it takes those bytes and just translates it to hex, and -c makes that in a more readable form. So we're going to print that out. Oh, I'm not in the right directory. Hold on. So we can see we have 52, 65, 74, 75, 72, 60, 2D, and 50, right? And you can see the ASCII representation of that over on the right, which is the entirety of that text is return path. So all the email files that we're dealing with start with the text return path, colon, right? So that's probably going to be a pretty good identifier for any one of the email files that we're looking for. So the tool specifically that I use for this challenge is called Scalpel. And the main way to modify that is by modifying its configuration file. So you can see where to go here. So scalpel/scalpel.com. So what we want to do is go into this. You'll see that there is a lot of information in here. So these are all common file types and headers that you can uncomment if you wanted to look for them on your machine. But we don't really care about that because we have a custom file type. So what we're going to do is we're going to say, okay, this is, we're going to say it's it's an email file. Yes, here indicates that it is case sensitive in terms of the headers. This number indicates how many bytes we are reading from the file after the header. So if we don't specify a footer, or I think even if we do specify a footer, if it goes over that byte range, it will just stop reading to avoid runoff. In this scenario, the footers for these files are all different. They're not consistent based on the format, so we're not going to worry about defining one. What we are going to format is that hex dump that we just had for the header. So that's what this is here, /x, whatever that digit was, to define our header. And then we're going to add that to our scalpel conf here. Okay? So the next thing that we can do then is once we have that in there, we'll probably have to remove the output file. So I'm going to do this. Okay. So there's actually, you can use Scalpel without mounting the image or with mounting the image. I'm going to do it without. So what this looks like here is we're just defining the output directory. -v is for verbose. It just provides more detail when it's running. And then we specify the .image file that we're running on. So it's going to run. Should be pretty quick because this is only a 100 megabyte file instead of 30 gigabytes, which what this was originally, which would have been forever. Okay, so this is good. So we see already at the top there, email with header, 7 files found. So now let's go ahead and let's go to our output. Let's take a look. Okay, so we have the audit.txt, which is basically what we just saw, and we have another directory called email00. Okay, we have those 7 files that it thinks it found. Well, let's just look at the first one. Okay. Okay, so there's the new employees one that we found before, I believe. Yes, I think that is the one that we were looking for. But yeah, so that's pretty much it. That's how you, there's some other ones too. This just goes through and you can look at all the deleted files that it thinks it found in the description. There we go. That's the one. That's actually the one that I was looking for. So it can't delete me. So scrolling through, you found the first one, which was actually on the image, and then here you found the one that was actually deleted, which was can't delete me, which was the return that Marzell sent that you did. All right. Now with that, I'm going to run through our next challenge, which is access logs, and then we're going to get to grant stuff, which is pretty far. So after that.
So Henry?
Yes.
To be clear, you had to make Scalpel recognize a new file type?
Yes, that's why I provided that image. So you had to define a new header for that file, which like it has a lot of common ones that are up there, but that are in the configuration file already. But in this case, I wanted you to find the header for that file and then print it out yourself for that one. So let's see. Oh, I remember. So this challenge was why is homework always in the cafeteria? So this one had to do with access logs. So you were basically given the description of an access log. So in those emails, he was trying to get a new badge for him made at the badge office. So Shane thinks that he was able to get into the building using this badge that he had created for him by spoofing the email and so forth, right? So now he's giving you access to one of the logs for the company of the whole month with all the door codes. So you're given the ID and the email that was sent previously. You scroll up here. You're looking for this email, or this email, this address right here. No, copy that so I have it clear. So what I suggested for people when they open this up, this is what you see. It's a lot of information, right? And it's thousands and thousands and thousands of lines. But the information that you're given is that what this represents is a timestamp, a comment badge access format, and whether the employee was allowed or denied into the building. So what I recommended for people with this challenge, and I will pull up actually my write-up for this, was that people start to dissect what this means before they jump into the problem. So one of the first things that you'll see is that there is kind of a switch where it goes from what looks like hex to binary. So that's probably going to be the cutoff between your timestamp and whatever that common badge access format is, right? So if you do a little digging and do a little translation, you can find quickly that that badge access format or the timestamp, we're just taking hex, right? We translate the hex into an int, and then in the datetime library in Python, you can take that int value and translate it into an actual time, which is in the Unix epoch time, which I did not change. I did not modify the time zones. And so doing that, we can translate our timeout. So with that information, you can pretty quickly, the easiest thing you can do is take that badge number that you were looking for, right, and hit Control F. What's the first record that I found? All right? You take that first record, copy the timestamp, translate the timestamp, that's your first flag. The next challenge that you have is to figure out whether or not, figure out the 2 times that one or many times that the intruder was denied access to them next to a room, right? Because you want to know what the attacker might be trying to get into. So it's important that you know what rooms he tried but could not get into. So this has you figure out basically the rest of the format. So we know that the first 16 digits are just a hex value for the time. We know that there's a common badge access format and whether the user was access allowed or denied as the next 2 things. If you search common badge access format, you will find 26-bit whiteout as the format. This was literally the first Google search. So 26-bit whiteout is literally a 26-bit binary number. This is the reference that I used when creating this challenge. It has a start bit and a stop bit, which is basically literally just 1 on either side, an 8-bit facility code and a 16-bit user code. So that 8-bit facility code is what I have coined as our door codes, and then our user code is the badge IDs, right? And so with that, we know that there is only 2 more bits left for this format, which is our 2 bits at the end. And if we do a quick scroll through here, see a lot of 1s, but you can see here 0, 0, right? More than likely 0, 1 is going to be access allowed. More than likely 0, 0 is going to be access denied, because those are going to be the less common times, right? So for this problem then, the main thing you need to do is just, okay, let me scroll through here. Okay, there's one entry where it was denied, right? Let's record the timestamp and move forward from that. There's another one right there. The other thing I asked you to do with this is I gave you an Excel file. And in this Excel file was the door code that I talked about, that 8-bit facility code. the access level required to access that, which really doesn't matter for these challenges. The space description, which is the door description, and also the layout of the hierarchy of how you get from one door to the next within Razor Power Company, which is important for the next challenge. So the final challenge description that we have, I will pull it up real quick because this one's a little bit more important. Is it Employee Policy Manual 5? Keep your badge on you at all times. So, he obviously got into the building, but we haven't, if you notice, when you were going through the door codes, that we were not able to find another time when that badge accessed the building again. So something happened. He did something when he was there the first day. Shane thinks he might have cloned somebody's badge. All right? So your objective is to figure out, okay, what might have led him to clone a badge? What indicators might there be that he cloned a badge? So the various hints that I gave for this challenge revolve around 3 or 4 different things. 1, translating the logs into a more readable form. 2, the door tree, the badge format, and the series of events. One thing you're going to know is that this is going to have happened after the last challenge, right? So we can already throw out a lot of logs just by looking at stuff that's after the previous event, right? Anything the day after. The next thing that we need to look at is, okay, we have this access level tree here of how the floor plan is actually laid out for the company. Well, if an employee is coming into work through the main lobby, right, which is the root of the tree, then they have to get to the office, like office 001, they have to go through main lobby 2, the IT department, and then to office 001. And if they want to go back out, they have to go back through the same things, right? So they have to have a valid path going from one end to the other. So there's really 2 ways you can go about solving this problem. One, you'll also notice that there's only 11 different employee codes in this list, which is why it was limited to 5 responses, so you can't just brute force which employee code it was. I'm just going to try to find. What was I saying? So what that means basically is that since there's only 11 codes, there's not like 100. You need to basically start looking through sequentially how you can do this. So the easiest way, I think, is by devising access log challenge. Is by making a function to translate it. So this is actually the code that I used. If you never use Google Colab, these are really useful notebooks. These are just Python notebooks that run on Google servers. Really easy to use. So this is a definition of the tree. That's how you made the logs. But devise something like this. So this function here translates the logs into a more readable format. I'll try to zoom this in a little bit more. So using something like this, and then also devising one of the ways that I came up as a solution to solve this problem is using a function like this. So I'm going to walk just briefly through this on how it works. So this validate employee movement function, what it looks for is it takes the initial log file and it sorts it by employees, right? So we want to look sequentially at each employee and see every movement that they made down the tree or back up the tree, right? To make sure that they're not jumping from place to place. Because if someone cloned a badge, what you would see in the access logs is that someone's in 2 places at once, right? So they might be on the upper half of the tree and the bottom half of the tree at the same time, which wouldn't be allowed, right? So we would have someone in the finance department, but then 2 minutes later they might be in the engineering office. But you couldn't do that without going back up to the main lobby and then coming back down to the engineering office. So what we check for here, all this is doing is we're reading in the log file, we're taking the log file and we're parsing it into a more readable format, into this variable parse logs. And then we're grouping those logs based on the badge code, the employee code. So that way we have a timed list of every code. And then for each of those, what we're gonna start doing, we're gonna sort those entries by time, just to double check and make sure they're in time order. And for each of the entries in that, which is each door they accessed, what we're gonna check is the parent, the sibling, and the children nodes of the last node. So we check the last node that they went to. So that's gonna be this if statement down here. Dum, 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 dum. So if the last node, so what we're looking for is to see whether or not that last node is a child, a sibling, or a parent. If it is not any one of those things, then there's no way it could have happened, right? So with a function like that, run this, and run this file, you can see that there's only one badge code that pops up as illegal. And so what you'll see is the last node, Engineering Office 102, is not a child, parent, or sibling of the hallway entrance to control areas. And so we can check that. Well, Engineering Office 102 is here, and the hallway entrance to control areas is there. So there is no way that someone could hop from that place to that place without going back up the tree. So something obviously is wrong there. You'll also notice, there we go, in this, that all of this occurs within the same day as well, which would be, as well as you can see the timestamps, 9:32, 10:30, 10:40, it's all very close together too. So which would be typical of someone having with a clone badge, coming into work, same time as someone else, and you'd have conflicting logs at that time period. And so the key for that challenge was the badge ID of whoever the intruder was. And so that was this badge ID, which corresponded to Homer Simpson. Or not Homer Simpson knockoff for Razor Power. Alright, so that was a lot of blabbing from me. And Grant, I know, wants to talk about his malware and reverse engineering challenges. So that was the final one of that series, and that brought you to, what is the name of that challenge? Was it USB?
It's USB, I can't remember.
I'm pretty sure it is.
Yeah,
USB infiltration. So that brought you to this, which is our next challenge here, which basically the endpoint monitoring system at Razor Power Company found captures any USB inputs or USB transfers into systems, right? And so you here are given a sample of a PCAP from a USB stand. So, which these are kind of interesting. I totally want to share it.
I can go.
Okay. I'll let Grant show it, and then he'll get to his reverse engineering challenges. And if you have to leave, don't worry. We're recording this, so it'll be available later as well. Yeah. Yeah.
No.
Okay. All right. Now we're going to hand it off to Grant.
Alright, yeah, so for this next challenge, the attacker has physical access to Razor Power Company's campus, and one of our endpoint monitoring systems managed to flag a USB transfer into one of our systems, which was the SCADA water system, I believe.
Yes.
So if we download this PCAP, a lot of people don't know Wireshark can actually grab transfers on USB transfers. Like most people are familiar with it for
Network transfer.
yeah, network traffic. But oh god, why does it look like that? Okay. Anyways, so here in a USB PCAP, automatically the first thing we should be looking at. Once again, I'm going to try to go pretty fast because we have a lot to get through. But we're looking for file transfers. Files are going to be pretty big, right? So if we sort by length, to the top. We have a bunch of very large packets using a protocol called USVMS. And this challenge is asking us the file type that was transferred and the number in the packet where the transfers began. So if we go through these really large packets, we go to the first one with that really big length. You go down here, you see ELF. That's an executable and linkable format. That's an executable on Linux that was transferred onto the OT system. So for the flag, you would simply have ELF, 9416, which is the packet number transfer began. All right. And then from here, we begin analyzing the ELF file that was put onto the computer. So for this, we have a file called daemon, which is actually, that sounds really sinister, but kind of a normal name for just processes running on computers. For this, I like to use IDA. Oh no, it's doing the thing again. What did we do last time?
Change the resolution now.
Change my laptop's resolution?
Yes.
Okay.
To 8. Go to settings.
Display settings. Wait, I'm on 1080.
I think it was scale actually. Go to like, yeah, go to
Recommended.
Okay. Will that make it? I don't know if that's gonna make it better or not, but we'll see. All right, so let's go ahead and start disassembling this. And fun little Easter egg about this malware, its code name during production was Sucksnet. That's what I like to call it. So, where is this? Demos. It doesn't have an extension, so I gotta go to all files up here. All right, let's open daemon up. So, what the challenge tells us is that it appears this is some type of armored malware, which means it has an encrypted payload that it decrypts at runtime. So when you're unpacking malware like this, the first thing you gotta do is figure out what's the decryption key so that we can figure out what this file is hiding. So if we go to main, this is a Go file, so it's statically compiled. It has a lot of functions in here. Where is main? There it is. All right. If we go to main, automatically, is that readable? Automatically, I'm seeing a lot of interesting function calls. We see get OS version. We see a function called get CPU info, get hostname, compute MD5, concat string, and then if you go down just a little bit further, once again, having to go pretty fast here, we see AES decrypt. So that tells us, and these are user defined functions, but we can verify it's actually AES decryption when we see here crypto AES new cipher, which is a Go crypto library. It's a function from it. But going back here, all that information, do you have any ideas as to what might be going on here? Just based off function name calls alone. It's getting information about the system it's running, concatenating it together, computing the MD5 hash of that, and then calling a function called AES decrypt. So one thing to note is that an MD5 hash is 32 bits, which is coincidentally the perfect size for a key on an AES 128 implementation. So this challenge would have you go into the SCADA water system, and once again, we can go into these functions and actually verify what it's doing, like it's reading from this file on Linux, which gets us our OS version and stuff like that. But once again, for the sake of time, going fast, my write-up will be much more detailed when I post it. But basically, the person that solves this, you would have to go onto that system and actually find all this information yourself, put it together, and hash it to get the key. But if you know anything about AES, you don't need just a key. You need something called the initialization vector. And you could actually have just grabbed that right here. These are put together to form the initialization vector. And it's also worth noting that this is in little endian format, so you actually have to flip it and put it together. But that would be your ID. And once you grab those, oh yeah, and here are the actual strings you would have pulled off of the system. Then you could hash that, which I guess I can show hashing that real quick. So like one way you could do that is, oh, I didn't copy that. Well, while WSL was, you can copy that. I can do echo, and then just echo dash n, I think. And then pipe that into a command called md5 sum to get the md5 hash of that. And that gives you the decryption key. And then you would put that in as a flag, and I already have the ID posted in the next part of this challenge, but going on to the next part, once we have derived, the first challenge is make sure you can get the key in the initialization vector, and the next challenge, we are actually going to extract the payload and decrypt it. And out of the 5 steps of this is probably the hardest step, figuring out where the payload begins and ends in the malware. So let's go into IDA and figure out what's being passed into AES decrypt. So one thing that stands out when you first look at this is there is some unknown reference location. And if we double click on that, that takes us to the .ro data section of an ELF file, which is the read-only section. And what this is usually this area is for like static and global variables. And if you look, this goes on for a long time. So whatever this is it's really big. So I would be willing to wager a bet that is our payload. And this is the length of our payload. And what these 3 instructions essentially are it's loading the address of the first byte of the payload, and then it is moving the length into ECX to use as a counter, and then these instructions are repeated however many times is in the counter register, and this would copy over all of the bytes. So if we want to extract this payload ourselves, we need to figure out where it starts. And to do that, we can first go to Edit, Segments, Rebase Program, so that the very beginning first address in this program is 0, so everything's an offset. And now when we go to the location of our, which I'll call this payload, I can press N and then do payload address. Here, CD020, that is the starting address. And then, wait, I did something. And here, that is the length of our payload. But it's worth noting that the move SQ, the Q stands for keyword, which means we are moving 8 bytes at a time. So it's actually how many bytes we copy is 8 times that number. So you can convert this to decimal, multiply by 8, and then you can use a tool like DD to extract it. So you can do DD IF, the input file, daemon, which is the malware itself, output file, extracted array. The BS is just block size, we're just going 1. The skip is that starting address, that's that 0C whatever. That's where we start in the file to start copying. And then the count is 8 times that number we saw being put into the counter register. I'm not gonna run this command because it takes a little bit, but I actually have already placed in this directory the extracted array. And then from there, all we have to do is use a command line tool like OpenSSL to decrypt it. Oh wait, wrong folder. that will give us a decrypted payload. We run a file on it. That's an L file. And then I believe it asks for an MD5 hash of it, so you can just run MD5 sum on it. And that would have been your flag. You wrap the hash right there in flag. That was probably the hardest part of this whole process. And then from here on, the third part, it talks about packed malware, which is a technique where you compress the malware's payload and add another stub. So this malware is like an onion. There's lots of layers of obfuscation to it. But it's asking you to unpack it. And a lot of malware authors will be lazy and just use out-of-the-box stuff that does it for them. So one thing you can look into is a lot of these packing softwares leave artifacts within the L file itself. So if we run strings on it, a strings decrypted payload, it's gonna give you a bunch of garbage. But if you just scroll for a little bit, and honestly you could have figured it out just Googling famous packing software. But if you scroll for a little bit, where is it? You'll see a fairly long string of human readable text. And the reason all this is jumbled is, once again, it's compressed data. So, all right, randomly Ubuntu. Oh, interesting. This file is packed with the UPX executable packer. You could have gone to that website, downloaded it, and then simply to unpack this, all you have to do is do UPX-D to decompress it, and then decrypted payload.bin. And now it is uncompressed and can actually be further investigated using IDA. And I think once again, this, you just have to submit an MD5 hash. So once again, you'd run that same command. All right, malware analysis 4 and 5, easiest part of the whole thing. We have gotten to the bread and butter of what this is doing. So now we can open our newly unpacked decrypted malware and actually see what it's doing. So I'm gonna open IDA again. New. And then we can go to all files, open, wait, wrong directory there. Decrypted payload. I accidentally left a debug statement in the malware. So that was a fun little Easter egg if you tried to run it on your own machine. And for those of you that can't see, it says cracks knuckles, it's mod busting time. All right. Okay, good. I want to make sure all of you can read it. And shout out to Gideon, because obviously the mod buster king himself helped with this. But the first question was simply, we're trying to figure out what the malware is doing, and we want to know the function it's using to connect to an IP. So we are wanting you to enter the function name along with the IP address and all that good stuff, which you could pretty easily see here. There's a function called modbus new TCP, which creates a new TCP context, and you can see right before there is an IP address being passed into that function. And you could write that function name with all of its parameters. And once again, the beautiful part about this is we can just straight up Google these function names, and like all their parameters and stuff, like in the documentation, will be the same in assembly. So we just have to look up what it takes as input. So as you can see, it's taking an IP address and a port. So we would, for the flag, we would simply put modbus new TCP, whatever IP we found and whatever port we found. And that was that challenge. And then for the final part, we know it's connecting to the IP address, but what is it doing to the water cooling system? And then once again, we would just go and look through these function calls, see one called write registers. And this is writing to the registers of the cooling system and turning them off, right, Gideon?
Yeah.
Yeah. And this malware was actually causing like a lot of the havoc that you were seeing. And there was a twin of it. There was actually 2 of them that you didn't analyze. The other one caused the meltdown, right?
Yep.
Yeah. So this malware actually was doing stuff to our simulated SCADA systems and like infrastructure. But that was the end of the main story up until the point where we were doing meltdown, right? Are you guys still going over meltdown?
Yeah.
Yeah.
All right.
Woo!
Once again, I went really fast working on write-ups that will be much, much more detailed explaining what's going on in terms of all these.
And that is the case for most of these. Some of them are already on the GitHub.
And if they're not, yes, they will be soon.
This one will all also be fairly quick, but
Yes.
the first thing
Yeah.
So y'all are going to upload the write-ups to
Yeah.
Yes.
Yeah, and along with the challenge files and everything.
Is it just like the most popular ones that y'all are discussing today, or literally all of them?
We're just going to go through at least the main story now, which is what we're about to finish up. And then we might have time for another one.
Are you asking for today or for the total write-ups?
The total.
Total will be probably main story and then
The most popular
popular
ones.
picked ones on
Yeah.
the survey.
Like if we had a survey, people asked what they wanted to see write-ups of, and we'll do those ones. I'll try to do as many as I can.
I was about to say,
I know
AKA
people had a lot of questions about mine.
AKA all.
And I've got
all
some
of
demos
these
ready for
challenges.
some of mine that people had trouble with, ready.
I think we're doing, like, anybody who wants to do a write-up, any of the GMs, as long as they want to do it, they'll do a write-up.
Yeah.
It's not gonna be based on like the top.
So if you want someone to do it, pass it through them.
There you go.
The write-ups take a long time.
Yeah.
All right, let me. Yeah. Okay, so this is the final step in the sequence. This is where it all goes down. This is where nuclear meltdown occurs. So this challenge is a little bit. What's the? Oh, also train.
For those of you that don't know the lore, our SCADA engineer for Razor Power Company was Wesley, who loves trains, although his name for the company is Tiberius Ironbolt.
And this train is the big boy.
The big boy, yes. But
Pretty apt name for a train.
But basically what brought us to this point is the water, you stopped the water system from being shut down, and now the meltdown is occurring. So for those of you that were there, a bunch of sirens went off in the building because the meltdown was occurring, and you had to go into Tiberius' SCADA machine for the control rod room and figure out how to fix the controls, which is what Gideon's going to go over.
Yes, so yeah, this is a very different challenge for many reasons. So most people, I'm assuming, haven't interacted with OT or ICS related environments. So that makes this a bit of a, very a doozy. A lot of new stuff. That and that there's sirens going off. So this is overall a pretty hard challenge, but hopefully this will help demystify some of that. So first, I'm going to pull in reference the actual challenge sheet. So we added, in the midst of the challenge going on, a bunch of different questions to kind of help, since this is a time crunch situation. You're not going to have the normal amount of time you would to be able to kind of sit and think about a challenge for an extended period of time. You have a 2-hour time crunch. And so as we were unrolling, or as the challenge was ongoing, we added more and more questions to the challenge description itself. And so we're going to use that as reference to kind of guide us through working through this challenge. So yeah, lots of different stuff here. So first thing, you're given username and the password to log in. I've already done that, so skip that. This is probably your biggest friend during this whole challenge set, is the documentation for the SCADA software itself. So yeah, given that the probably 99% of people who competed in the competition have maybe not even ever heard of SCADA before, much less have interacted with one, this is supposed to be the bread and butter for helping solve this challenge. And so let's go on and kind of answer some of these questions. So the first question is, what IP is the nuclear process on? So well, I guess before that, I'm gonna go ahead and open up what the SCADA actually looks like for those of you who didn't get to see it. So whenever you open the desktop, you're greeted with this how to open Designer Launcher, and we're gonna go ahead and follow these instructions to the T. So we go to Downloads, Designer Launcher app, and then we run designerlauncher.sh, give that a brief moment, and then we have our Ignition Designer Launcher. So what is Ignition? Ignition is the specific brand of SCADA that we used as part of the challenge. This is also a pretty much ubiquitous SCADA software in industry. So you're actually, this is a cool opportunity to use some real software that's being used out in the field or out in different industries today. So cool little fact to slide in there. So we're gonna open up the designer. I just double clicked on this Ignition SCADA control. I probably should define what a SCADA is, shouldn't I? Also preface, this is me gonna be trying to speed run this like Grant did, but there will be a write-up for this in case there's any questions. I'm also gonna put in a brief excerpt about kind of ICS systems and OT systems in general to kind of give you some backup information, since for many people this is a new, maybe a new field that you haven't interacted with before. So SCADA stands for Supervisory Control and Data Acquisition. What the heck does that mean? Great question. So what it means is the SCADA serves as your virtual control room for monitoring what's happening in your field. So in this case, it's a nuclear reactor, and so there's a actual nuclear reactor on their grounds, right? But in order to monitor what's going on, it's probably not feasible to have someone, or maybe in our hypothetical instance, maybe they could, but it's gonna be very advantageous to be able to monitor what's happening in your system at various places within your campus and also beyond your campus. And so what the SCADA is that control room itself. So sensors monitor what's happening in the reactor. Those sensors send information to the SCADA, and the SCADA displays that information, as we will see in a second. So does that make sense on what a SCADA is? Okay. Yeah, if anyone has a question, please just speak up and ask. This one is a bit of a doozy, like we said before, so. Okay, it would help if I could type. It's the extra zero. Yeah, it's always extra zero. So yeah, this last line says unlimited power. So it's this one that says unlimited power right here. You open that. Fingers crossed that the connection doesn't break.
So were there actual alarms going off during this point? Like,
Yes.
that would have messed with me.
What was unfortunate too was the alarms were a lot more high pitched than you would think. So we had to we like turned them up, and then it was like ear piercing, and we turned them back down. It was like, well, we'll just make them flash, and then if you get near, then you can hear it. But yes, lots of alarms, crazy stuff going on. So, okay, at the bottom it says trial expired here, so this is not necessary to the challenge, but if I type in this.
There's usually a paid service, so we use the trial version.
Yes, we use the trial version because we are mere students. And it's like $10,000 for an actual license.
Yeah.
So not the kind of cash we can afford, so we just we gotta click a refresh trial button every 2 hours. But anyways, okay, here is our wonderful SCADA. So we have this thermometer looking thing here. We got this red looking tank with bars in the middle. Got this pump with a red exclamation mark. That doesn't seem good. We have this looks like water. We got some more pipes coming in and out. So okay, a lot of different stuff going on. So this then leads us to okay, when we see that this is the SCADA. So now we kind of go through our questions list to kind of use that in order to probe on figuring out how the SCADA works, because that's really what these questions are designed to do, is to get you to navigate through the guts of the SCADA environment itself and figure out what's happening. So if we go back to our list, first one, what is the IP of the nuclear process on it? So, and then in parentheses, this can be found in the gateway. See the docs for what the gateway is. So I will go ahead and open the, oh, this opens within the thing. Oh, that's interesting. Okay. So, like I said, the nuclear process is the actual nuclear reactor that's on site itself. So, since the data is being sent from the nuclear process to our SCADA, they're communicating over Ethernet. And so we're figuring out what the IP of that server that's sending the information to our SCADA is. So I have actually what I'm gonna do is, I'm gonna pull this up in a separate view. So I have the challenge here, copy and paste this, and open this. Okay, so the question was, what is the IP, what is the IP of the nuclear process on? Okay, well, you know some about IP addresses, devices. I don't know if this is confusing. Let's just get an idea of, okay, well, what is the gateway? So if you're overwhelmed, you just, and this is the first page that it'll take you to. It's like, okay, actually we'll take you to the designer, but here's the platform for the gateway. So yeah, briefly, so the designer is, just to make sure we have this clear. So the designer is this thing where you actually see the SCADA itself, and then the gateway, as if you read the documentation, is this web interface itself. And so, given that in the challenge description it says, okay, well, it's somewhere in the gateway, then we need to figure out what is happening in this gateway screen. So if we go to these documents, scroll down, okay, we see a section called home, okay, a section called status, that seems interesting. Oh, there's something about connections, known devices, okay, that seems interesting. Okay, there's also a section called config. Okay, so probably should start diving through some of these and see if it has anything useful. So we open up that status, we go to that device connections that we saw earlier, and we see something called control rods, okay, communicating over Modbus TCP, which was also used from the malware earlier. Okay, definitely item of interest. You see on the side, we see an action, it says details, scroll down, okay, I don't see any IPs here. At the top right, something called configuration, okay, we click that. See something called addresses, let's click edit. Okay, we have our host name. So what this is within the config menu of the SCADA itself. And this is where lots of different stuff is configured, but specifically device configurations can be set up. So at the top, we see this little path where it says config, OPCUA, devices. Depending on how you use the docs, you can reach this view as well. We go to, where is it? Go to config, go to gateway settings. Basically, it's a pretty open-ended thing. You can use the search bar, search up different terms. There's many different ways to go about it. Kind of an all roads lead to Rome situation, but you've successfully figured out the first question, which is, okay, what is the IP process on? And then you kind of iteratively go through each of these questions to figure out more and more of how the SCADA works. But for the sake of time, I'm going to show the solution, or what you would have figured out after solving each of these questions. And like I said, this will all be in the write-up, so if you want to know something more about how these different things work or each step of the question, then that will be there. But for the sake of showing the solution, so what you would have learned going through the question step by step is that there's a very important section which is right here in the tag browser. So one of the questions is, what are ignition tags? And essentially, what they are, in short, is, so whenever the SCADA pulls information from in this case, our nuclear process, and it's storing it somewhere, okay? And the tags are where this is being stored. So we can see that we have this thermometer that is showing us the temperature. So over the course of the 2-hour duration that was given for the emergency scenario, this, we're running out of time to show the math.
No.
But basically, there's a lot of math. we put more work into the math behind this than we should. But basically, it's somewhat exponential, where it slowly creeps up, and then towards the end, you reach this critical zone, it starts turning red, things freak out, and then, yeah, nuclear meltdown. But we can see, though, that although everything's kind of aired out over here, we are still pulling information about the temperature. And it's like, well, okay, that has to be communicating with the device in order to get to that. And we can see that over here on the left-hand side, we have this tag browser, and we have these different values. So we have core temp, heat X pump flow, rod depth 1, 2, 3, 4, 5, and then steam outflow. Okay, well, considering this is pulling information, let's open this up and see what we can find. Well, okay, I don't really know what any of this means, so, okay, well, maybe we can see the difference between this one that is able to pull information and one of these other ones that are aired up. So, okay, take a quick look, memorize everything that's here, okay? Okay, it's okay if you don't do that, but, so.
Screen cap.
Yeah, exactly. And then we go to one of these next ones that's aired out, and for the astute eyes among you, you'll notice that this OPC item path is blank. So, okay, that's clearly something of importance. So you can see if you look at the previous one, it says control rods and then HR09. So control rods being the name of that device from earlier, and then HR09 meaning the 9th holding register from the Modbus server. So one of the questions in the list was what protocol is being used to communicate. That protocol is Modbus TCP. How data is stored, analog information, meaning something that's not a 1 or a 0, is stored in the form of these holding registers. So in this case, by default, you can see that it's pulling the 9th holding register. And if we go to on the questions, one of the later statements is that it's ordered sequentially. It's ordered sequentially from left to right, with the core temp being the last value, meaning that from left to right, that if this is the 9th, then that pump all the way is going to be the 8th value, 7th, 6, 5, 4, 3, 2. And so we can apply that same logic and just go through here and enter in, or I guess,
You have to do something with the heat pump flow first?
So what we're going to do is go through and first copy the syntax from this item path, the control rods, the HR09, and then iteratively go through and try to assign it to the correct holding address, as given by the hints in the challenge in the challenge description. So start here from the right with this. All right, well, we'll start from the left. So this is the rod. This is rod 1. We can verify this because at the bottom under props, more information like this might. I'm going to be jumping some leaps in logic while I'm explaining this, but this is going to be more explained during the item itself. Is that these tags are bound to the actual components via this binding, and we can see that in the tag path it says rod 1 depth. Don't worry about what the little default thing means there. The important thing is that it's bound to rod 1 depth and so on. So if I go to rod 1 depth, paste this in. Remember I said that this is it increments from left to right, and the temperature being the last one. So this one is 2. As you can see, when I press enter, fills in. I'm actually really glad that they animate it instead of it pop in and it fills in. I thought that was pretty satisfying, but maybe I'm just weird like that. 3, 4. Get it going. 5. 6, 6. Then, so this one is the, if you click on the name, this one is actually the heat exchanger pump. I wish it showed the name instead of doing that notice. For some reason when it does 2 notices, you like are not able to see the name by default, but if you go in you can see that that's actually the heat exchanger pump. And yeah, and the way that we set up the challenge too, this wasn't a all or nothing. This was something where the more of the answers that you got right, the closer you were going to get towards the total score. So if the logic didn't make intuitive sense of, okay, how do I know which value goes to which, we didn't really count you off for that. It was more so understanding that the tags are associated with components, and you need to make sure that the OPC item path is filled in, so it's pulling information from that process, so you can actually see what's going on in the nuclear reactor. So I believe this is 7. This should be 8.
And you can notice the malware slowly pulling out all the control rods if you just saw the numbers change there.
Yeah, so yeah. Like we said, so it goes on this exponential curve over time and slowly increases the temperature. Well, the temperature increases as a function of the depths of the rods and the pumps. So yes, as Henry said, over time, if you were just to leave this sitting here, we would see the rods slowly tick up and up and up. And yeah, fun fact, in case you didn't know, the more up the rod is, the more reactive the reactor is, and if it's all the way down, then you're what's the word? You're slowing the reaction.
Yeah.
So you would see this tick up and up and up, and it's like, okay, well, everything's connected. How do I control what's happening? So if you just try and type in here, you can actually just go in and type in values, enable read-write mode. You can kind of do what you want. So
now you'll see the reactor temperature spike.
Like we said, now it's at, so this is in Celsius, this is 700 degrees C.
Does that mean we're all dead now?
We are all dead.
Yeah.
I just killed all of us by accident. Sorry guys. So we can kind of do with these values what you will, and you can see that you're now able to successfully control the temperature. So ideally, how we wanted this to happen was we started out at near critical and go up, but we just did it where we pretend the attacker, like, to test the functionality, set all the temp to 0 and just slowly ramp it up. So to solve this challenge ideally and to make it more visually pleasing, try and hit it within that little green range. So what I'm gonna do is just play with the values. And probably gotta make this a little lower.
Yeah, the pump flow kicked up, that's why.
You gotta get it just right.
But yeah, bring down the pump flow a little bit, yeah.
Yeah.
A little bit more.
Just like 40.
Oh, there we go.
Okay, so yeah, we're in like a nice green zone.
Which that is actually around the operating temperature for a reactor around like this is like around 350 degrees Celsius.
Yes. So we technically have stopped the attack because we're now able to control. Technically, in a more advanced version of this challenge, you would go in and like stop the malware. Not necessary to solve the challenge. This is more about understanding, well, one, kind of putting you in the mindset of someone in a live incident response setting. So, in a real world, if it was, okay, it reset. So, like I said, the attack doesn't stop. It's more about being able to establish control over the rod depths and the pump flows. But the idea and the mindset behind this challenge is to kind of put you in the headspace of someone who is, they realize that an emergency is ongoing, live, and kind of being quick with your feet. And so this is something to where this is supposed to be very hard, but for the purpose of kind of putting you in that mindset of, with knowing very little, like what to do from there. So to those of you who just even attempted this, thank you. And this, very hard
I
challenge.
hope you learned something. But yeah, I think the reason it resets is because
Well, it's the thing's still going.
so it's still going, but I think when you control it, it'll like keep writing to the Modbus server for a certain amount of time, and then it'll stop, and so that's when the malware kicks in again.
No,
And
the
it-
malware still kicks in because we.
Yeah, I'm saying the ignition like will like write for a
Yeah.
certain amount of time, and then when it stops writing, the malware will overwrite it again, and that's what happens.
It writes once and then
Yeah.
the thing writes it again.
Yeah.
And so,
Yeah.
So, the last part of the challenge is just they deleted all the controls. So, yeah, if you're an engineer and you're looking at this, unless it would be kind of cursed to control the rod depths by if it's like a touchscreen, like an iPad. You can drag the rod depths. That would be a little
Don't think
questionable.
that's how they do it.
So, realistically, you could put some sliders on the bottom, and then the same way how the rod depths are connected to the tags, you can connect some sliders to the tags, and that was in our mind, like the ideal solution was you have a bunch of sliders, one for each variable of control, and then have it connect up to the tag of interest, and then it'd be able to demonstrate, hey, I can drag this and it'll adjust the depths, and I can put it in green or in red or wherever. Just be able to show that you were able to, one, understand that it's connecting out to some nuclear process via Modbus TCP, be able to understand what ignition tags are, be able to understand how they connect to these components visually, and then how to establish control over them. So, yeah, there's not a flag for this. It was manual verification just to see how far you could get in this sequence. It was 2 hours emergency incident response. Didn't want to be an all or nothing endeavor, just to try and just to kind of have some fun with some software that probably most of you haven't seen before. But yeah, that was the meltdown, and that was the end of the main story. So yeah, hopefully that was enjoyable. Whenever for competition.
Thank you guys for sticking around on your Halloween night.
Yeah, thank you.
For some of the problems. But yeah, we'll have write-ups on all the main story stuff at the very least.
Yep.
All up on the GitHub, and then Greg's already got a bunch of other ones worked up. And then, Kate, do you want to do yours?
Yeah.
All right, we got one more for today. If you don't have, yeah, Kate's got her USB. Is this the dropped one, or is this Homer's reminders?
This is the disappearing data, so it's the USB one.
Okay, so one of the other challenges that we had was you had to find Kate's character, Mandy, who was in one of the offices, and she recently got into lockpicking, as it happens to be. And so you had to go find her, pick a lock, and then when you picked the lock successfully, she would hand you a USB. And on that USB, you would have to do some forensics to find some missing information. And so Kate's going to do this little demo, and then we'll wrap up here around 7 o'clock-ish. We'll call it good. Again, the video will be up on YouTube hopefully today or tomorrow.
Okay, so this is not going to be a full live demo because it would take too long. So, I'm going to close all this. Okay, so you can see this. Okay, so I just plugged the USB in, and as you can see, if you open it up, you see nothing. A lot of people came up to me and they were like, "There's nothing on the USB," and I was like, "That's what you think." So, there's a really cool tool, digital forensic tool called Autopsy, and that's what we're going to be using. What I did was I put files on here and then I deleted them, and so it looks like they're gone, but they're not actually gone. And I could explain, to keep this short, I could explain what's happening. You're not actually deleting the files. When you delete files, you're just deleting the pointer to the memory address, so then it says it's deleted, but it's not actually deleted until it gets overwritten. But anyways, okay, so it looks like the USB is empty. It's not actually empty. So if we exit out of this, if we open Autopsy, this is after running it. This actually takes a bit of time. So I ran it earlier. I don't know if anyone saw, my laptop was here and I came and grabbed it and I accidentally pulled the dongle out. So it wasn't finished running. And so usually after Autopsy runs, this is what it looks like when you open everything up. And it looks like this. It looks like Homer 1 PNG, but usually when you select it, it'll show the picture right here, but I did stop it in the middle of running. So it didn't finish fully, but that's okay. Because all that's missing is the file right here. So you get here, you see all the files, and there's 17 total files. And so what you can do is you can go download them, and all you have to do is just click it, and then you say extract files, so you'll extract the files. Once you extract the files, you can open them up, and you'll see a whole bunch of fun Homer files, or Homer pictures. Some of them are even GIFs. That doesn't matter. What I wanted people to do is look at the metadata. And so if you open it up and look at the metadata, there's some really cool tools called Exif Tool. Also, if you use Exif Tool to like put things in the metadata, it'll say Exif Tool and places in the metadata. So I was hoping that people would like open it up, see that it says Exif, and then know that it's something in the metadata. But the very first one, I already like pre-did this. This is homer1.png. If you look, you'll see in the copyright field, I wrote over it, and I wrote an F. And so I was hoping that people would see that there's an F, and then think, oh, maybe this is the start to the flag. So, and then go on to Homer2, scroll down, look at the next copyright, see that there's an L, the next one, see that there's an A, next G. And then if you do that for all 17 files, you'll get flag not deleted. So that's it. That's all I wanted to show.
All right, cool.
Yeah.
Well, I guess that will wrap us up for RazorHack 2024 main storyline. Challenge descriptions. But yeah, we'll have the write-ups on the GitHub, which we will link, which I already linked in the general chat. I think mine should be up there already, and I have one other set of challenges that were some OCR related ones that I will post at a later date that were a little difficult. I think that's the most of mine, and Grant will have a bunch up too. But thank you all.